All right, are you sure? Measurement and significant figures. We're going to look at where does significance come from and how we can deal with them. First thing we need to look at are measurement errors, systematic and random. Those are the two types that we'll be looking at. Systematic errors are those that continually show up throughout your entire experiment. They're in one direction, either high or low. Things like air resistance and friction could be a cause of some errors. Shoddy construction of your measuring instrument. Maybe you have a leak in the graduated cylinder that you don't know about. Maybe you are slow on your timing device. Your reflexes are slow. The shift of position that you've used to measure and to take a reading affects the way that your reading comes out. So all of those affect the accuracy, how accurate you are with a particular measurement, and those are systematic in nature. The shift of position is a systematic error, and this is called parallax. You eliminated parallax when you get down eye level with the graduated cylinder and read along that line, read the meniscus right there. Also, if you're reading, for example, this scale, if you're reading directly on top of it, you're going to be reading directly on top of it like this instead of from the side. You'll get a better reading and eliminate that parallax error, that shift of position. Random errors occur with the precision of your instrument is not what you need it to be. You're using an instrument that is not divided up into small enough units. Actually, environmental conditions can hurt you for random errors. The mechanical vibrations could occur. As we said, instrument limitations, dealing with the number of significant figures, and I'll show you some of those in a little bit. Misreading an instrument. So all of these produce random errors, and by eliminating random errors, you can increase the precision. Here's a look at accuracy, which by eliminating systematic errors, we can increase accuracy, how close we can get to the accepted value. We have a way of doing that with looking at or analyzing that with absolute error and then percent error. It's not a big deal, it's not a big calculation, but it's just something that we need to deal with. The observed is your value, it's your experimental value. The accepted value is just what it says. It's the accepted value of whatever measurement that you're taking. So let's take a look here. Here's an example in an experiment to measure the acceleration due to gravity. 9.96 meters per second squared is determined. What is the absolute error and what is the percent error? So the absolute error is equal to the absolute value of the observed minus the accepted. That's all that it is. And we'll take that as being the observed, which is the 9.96 meters per second squared, minus the accepted value that's given to you right there is 9.81 meters per second squared. Notice that I write the unit as well, because anytime you put a number, you got to have a unit. So here is the absolute error is 0.15 meters per second squared. So that is going to be the error that's involved. That really doesn't tell us much other than it's we were below that value, not interested in above or below, to tell you the truth. So let's look at the percent error. And the percent error, I'll do that in a different color. I'll do that in purple. How about that? Purple. So percent error is the observed minus the accepted divided by the accepted, and then we'll take the absolute value of that and multiply that by 100. It's very simple. It's just the absolute error divided by the accepted value. And so that's equal to 9.61 meters per second. Ooh, 9.96. Where did I get 61 from? 9.96 meters per second squared minus 9.81 meters per second squared divided by 9.81 meters per second squared. Take the absolute value, multiply by the old 100, and get a percent error of 1.5%. 1.5%. So that's not bad. In terms of a lab, you get a good grade on that. Precision is reproducibility of results. Just as I said, reproducibility of results. How far apart are those values? And by taking several readings and several measurements, you'll get a value for that. And this is important right here. This little statement right here. Large degree of precision does not necessarily mean that you are accurate. You can be precise without being accurate. Here is a target. Here is, we know that the accuracy is going to be the red dot. That's the bullseye. And out here is a grouping of shots, and those we've grouped together very nicely. We would call that precise, precision, P-R-E-C-I-S-I-O-N, precision. This we've done very nicely. We have it precise and we have it accurate. They're grouped together and they're right on the spot. So we'll call this accuracy and precision. And then right here, we are not grouped. This third one is not grouped together at all. But if we were to average those three, we would get an accurate result. So we'll call this accurate, E-A-U-C-A-R-C-Y. That's right. All right? So precision, they're grouped together. Reproducibility of results, and we got it right on the spot. Here, we were kind of off in our reproducibility, but somehow we averaged to get the right answer. Here's a precision example. Looking at two sets of data. Again, as I said, the spread of results is another way to look at precision. Precision here, sample A, set A, 100, 100, 99.99, 99.99. So if we look at the spread of results there, it's 0.01. Set B, 100.10, 100, 99.88, 100.02. So the spread, a low of 99.88 to a high of 100.10. That is at 12 and 10, so 0.22 is its result. Yeah, that's spread. So the more precise set of data is going to be set A. Second example of precision. Here we've got two thermometers. One reads 115 degrees. The other one reads 115 degrees. I don't know what happened to my little arrow there. But anyway, it's coming in right there. If you look at it, you can see it's coming in right there. So 115 degrees, well, okay. Over here, I know it's exactly 115 degrees. So it's 115.0 degrees. Here, I can't judge if it's 115.0 degrees. I can just see it's 115. So precision-wise, thermometer B is more precise. So with all of that, leads us to significant figures. And significant figures is something that is confusing to students. And you get to a level and you have the rules and you have what you can do with them and how you multiply them and so on. But if you don't understand what a significant figure is and where it comes from, then those things really don't make much difference to you. So by definition, a significant figure are all digits in a measurement that you are certain of, you're certain of those, plus the first uncertain digit. You estimate that. And the significant figures are determined on the precision of the measuring instrument. That statement right there, the precision of the measuring instrument, you better know that. You better know that because I'm going to ask you that. And anytime I ask about significant figures, precision of the measuring instrument better be something that you come to and answer with. I'm telling you, it's going to happen. So let's take a look here at these instruments. Here's a graduated cylinder. These all have different amounts of precision based on the divisions that they are. We can look at the divisions and estimate to the next division. What do you mean? What are you talking about? I don't understand. That's fine. So here, this is a graduated cylinder that is divided into 10. So there's 40, 50, 60, 70, 80, 90. The little half marks right here are simply a guide for us. They are not divided. It's just a guide. So this is divided into 10, so tens, so we can get and measure down to the ones. So I know that if this is my mark, that I have at least 80 milliliters in there, and 80 milliliters plus not quite 5, so I'm going to say 84. I'm going to say 84 milliliters. That's my certain digit. This is my uncertain digit. Uncertain digit. Take a look at this one. Here's a pencil. This pencil is measured 1, 2, 3, 4. These are all measured into ones. We'll call these centimeters since there's no scale or no units on these. We'll call this 1. Sorry about that. So now you see what time it is. So this is going to be 4. I'm certain of the 4.2 centimeters. This is my uncertain digit. That's my uncertain digit. Now we take now we're going to divide this into 10 parts. So this is all divided into 10 parts. So now I've got 4.1, 4.2, 4.3. But notice I'm a little bit past the 4.3. So I can go 4.3. So I'm certain of that. And I can estimate, and I'll say 4.31 centimeters. The 1 is my uncertain digit. Okay, you do this one. How's that? Which one is the uncertain digit? Look at this one. Now it's divided into 10 parts. This may be a little bit more difficult to see, but if you have good eyes like I do, you'll be able to see these here easily. So 4.4, and it's right on that guy, so I'm going to say 4.40. Don't be scared of that 0. Which one is the uncertain digit? The 0. And of course you got to have your units. Here's 1. It's a broken piece right here, so we're continuing this on, so it continues up to here. So this is going to be what? $11.65 centimeters. There's my uncertain digit, the 5. All right, let's try some more. How long is this green line? 9. I'm certain of the 9. And it's right here. So it's right on that 9 line. So it is going to be point, and it's between the 0 and the 1, so it's going to be 0. Now, I can estimate how far is it between the 0 and the 1, and I'm thinking it's right on it, so it's going to be 0, 0 centimeters. Don't be scared of the zeros. Don't be scared of the zeros. So this is the uncertain digit right here. That's the uncertain digit. And we're able to go down to the hundredths place because this ruler is divided into tenths. It's divided into tenths, and we can estimate down to the hundredths. And that's the way that that goes, is that whatever division that measuring instrument is divided into, you take and you're able to estimate to the next place. So this leads us to those rules that I was talking about, number of significant figures. But now that you know where significant figures come from, the rules should make a little bit more sense possibly. So number one, all non-zero digits are significant. So how many significant figures do you have here? 1, 2, 3, 4, 5, 6. Those are all significant, so you have 6 significant figures. Any final zero or zeros used after the decimal point are significant. So this zero, I put this zero here for a reason. It must be significant. So there's 3. This zero was placed here because of the measuring instrument that was used. So there are 4. These 2 zeros are here. This 0 right there was placed. It's a final 0 or zeros after the decimal point. They were there for a reason based on that measuring instrument. We've got 5. Number 3, zeros between 2 significant figures are significant. Here's a non-zero digit. There's a non-zero digit, so that 0 must be significant. There's a non-zero digit. There's a non-zero digit. That one must be significant. So we have 6. All zeros that are used only to determine the decimal point are not significant. In other words, I did not have to put, or excuse me, I had to put these zeros here to maintain the integrity of that number. If I did not put those zeros there, then it changes the value. Okay, so they are there for a reason, not because of the measuring instrument, but because of the magnitude. So these are not significant figures. They're not significant, so I only have 2. Same thing here. If I did not put those zeros, it would change the value of that number. And so those are not significant. So I've got 3. The term significant is related to the measuring instrument. To the measuring instrument. How many significant figures? Correct. 3. How many significant figures? Correct. 4. Final 0 after the decimal point, 0 between 2 significant figures. That's significant because it's after the decimal point, and that's a non-zero number. Correct. 7. Keep going. Look at these guys. Are these significant? Those zeros are not significant because all they do is tell you that it is 0.00006. It hasn't got anything to do with the precision of the measuring instrument. Now, this is a final 0, so he is significant. So we've got 1, 2, 3, 4, 5 digits. Uh-oh, scientific notation. Significant, 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 significant. How many is that? 5? $300. $300. One significant figure. If I did not write those 2 zeros right there, it changes the value of that number. And as a result, it is not significant. I had to put those zeros there to keep that number at 300. So when we add and subtract these things, there's certain rules of the sign as well. This is the one I love the most, and people get confused by it. The rightmost uncertain digit in sum or difference will occur at the leftmost uncertain digit of the add-ins. I'll read it again. The rightmost uncertain digit of a sum or difference will occur at the leftmost uncertain digit of the add-ins. It's very simple, very straightforward. Look, here is, and I'll change colors here. I'm going to change to purple. Here is 9.27 or 927.4 and 34 centimeters. These two were not measured, these two measurements were not measured with the same instrument, because this one is able to go down to the tenths place, this one only to the ones place. So two different instruments. So what we have to do is we have to be aware of that and know that we cannot just throw these numbers in together because they weren't measured with the same instrument. So the question is, okay, so which one is the uncertain digit in each of these? I guess 4 should have changed the numbers. But anyway, here we go. 4 and 4. Those are the two uncertain digits. Which one is furthest to the left? I'll change again. This 4 is furthest to the left. That is as far to the right, that's as far to the right as the answer can go. So I'm going to add this together. I'm going to get 4 plus 0 is 4. 4 plus 7 is 11. Carry my 1. 1, 3, and 5 is 6. And then, of course, a 9. So 961.4 centimeters. But this is as far to the right as my answer can go, because this is the leftmost uncertain digit. So this becomes 961. The rightmost uncertain digit in a sum or difference, that's adding and subtracting, occurs at the leftmost uncertain digit of the add-ins. And that's the two things or three things or whatever number of things that you're adding together. That is addition, subtraction. Multiplication, division is a little bit more straightforward here. It's which one has the least number of significant figures, and we put this in terms of precision, which one is the least precise measurement. So here is here's our one that we just did. So here's a product. If you multiply or divide by an uncertain digit, it becomes uncertain. That's the mechanics of it. What you need to know is the fact that here I've got 3 significant figures on this guy and 2 significant figures there. Which one has the smaller number of significant figures? Tick-tock, right, 2. So this guy's got 2 significant figures. So our answer can only have 2 significant figures. And here's the mechanics of it, and I'll just kind of go through. So if I multiply 7 times 3, I get 21. That's uncertain. 3 times 3 is 9, carry my 1. That again is an uncertain digit. I've multiplied by an uncertain digit. I've multiplied by an uncertain digit. I've multiplied by an uncertain digit. So this first layer right here is uncertain. Then I'll take and multiply 6 times 7 and I get 42. That's uncertain. But now I'm going to multiply 6 times 3, 6 times 4, and 6 times 1. These are all certain digits. These are all certain digits, and so the results are certain digits. And if I add these together, I come up with 905.31. That's an uncertain digit. That's an uncertain digit. This, since I've added it together, is an uncertain digit. Here, that's added together is an uncertain digit. And I've got my 9. So all the digits in a measurement that you are certain of plus the first uncertain digit right there. So we'd round that to 910 or 9.1 times 10 squared. Same thing happens for division. I'm not going to go through that. You can take a look at that and do that on your own. So let's find the area of this rectangle. There's our rectangle. Cute little guy. Here are the dimensions of it, 3.84 square centimeters and 2.12 centimeters. So I'm going to multiply these together. So how many significant figures am I going to have? I can have 3 significant figures because this guy has 3 and that guy has 3. Both of them, let me ask you this, were both of these measured with the same instrument? Yes, they were. Look at this. They can go down to the hundredths place. They can go down to the hundredths place. So they had the same precision of the instrument. So let's go ahead and multiply this. And Once again, we're simply just going to multiply. 2 times 4 is 8, 2 times 8 is 16, 2 times 6 is 2 times 3 is 6, plus 1 is 7. Same thing here, 4, 8, 3, 8, 16, carry my 1, 7. So add all those together, and this is what I end up with, 8.1408 square centimeters. And as a result of that, we end up here with 8.14 square centimeters. 3 significant figures. So from this, I hope that you got an idea, a better idea about significant figures and measurement errors as we've gone through this.